two things. First, we will think a little bit more about equilibrium, and then a few words about one of the questions on the previous quiz. It's worth a little bit more thought. So, remember, equilibrium means no accelerations of any kind, no meters per second accelerations, and no angular accelerations either. Hang on. Okay. If there are no meters per second accelerations, then that means zero net force, and similarly, if there are no angular accelerations, that means zero net torque. And we use the fact that equilibrium means zero net torque to figure out, we can use that to figure out the strength of various forces. For example, in this case here, you've got a steel beam and its mass is 1,000 kilograms, and it's supported at two places. Here where it's attached to the wall, and then here where there's some kind of a cable pulling on it. And we would like to know how strong how strong the pull is from the cable, given that it makes a 30-degree angle with the beam, and the beam has a mass of 1,000 kilograms. So how do you do that? Well, you start the same way as always. You see what forces are at work on this beam, and since we're thinking about torques, you must locate the point where that force is acting, because that'll determine the size of this displacement term, as you saw in previous work with torques. So, what forces are acting on the beam? There is, of course, the cable tension. That's the thing that we're trying to find. And then, of course, there is the weight of the beam. And every little bit of the beam has some mass, so it feels a weight force. But remember how we can simplify things. We can imagine all the weight, all the mass of the beam concentrated down to just one point that we call the center of gravity. And we imagine that the weight force is just pulling on that one point, just pulling on the center of gravity. Center of gravity you can think of as sort of the average location of all the mass, and if this is a kind of a normal beam, then the mass is spread out evenly over the whole length, so the average location of mass is right in the middle. This beam, we don't know how long it is, but it's got a length of L. We can call that length L. And halfway, right at the L over 2 point, there is the weight of the beam. So there's two forces, and there's one more. We know there has to be a third force because it's in equilibrium, and equilibrium means, among other things, no net force. So the tension is pulling this way, so you can think of that tension as having a vertical component and a horizontal component. This tension is really a sum of some vertical pull, call it the vertical component of tension, plus some horizontal pull, and the sum of those two components gives us the actual tension. So this really involves a leftward pull. You can think of this as the sum of an upward pull plus a leftward pull. Well, if there is a leftward pull because of this tension, and if the net force on this is zero, then there must be a rightward force coming from somewhere else to cancel out the leftward force here. And the only other place where a force could come from would be from the only other thing that's in contact with the beam, and that would be the wall over here. So we know there must be another force, a third force, from the wall on the beam, and we don't know really anything more about that force. All we know is that that force must have a rightward component that is big enough to cancel out the leftward component of this. So that force from the wall on the beam could just be a force pointing straight to the right, or it could be a force like that, or it could be even be a force like that. We don't know. Like I said, all we know is that there has to be a force there, and it has to have a rightward component, because if there weren't a rightward component, there would be nothing that could cancel out this leftward pull, and if this is not canceled out, then you do not have zero net force, and that means you do not have equilibrium. But this thing clearly is in equilibrium. So there has to be this force to cancel out this force. Now, what we're trying to do, remember, is calculate the value of that force. We know almost nothing about this force, and we're not interested in finding out anything more about it. So that means it makes sense to put the reference point, or the pivot point, right here, at the point where this force from the wall acts. I shouldn't say T, it's not a tension, it's some kind of force from the wall. So reference point or pivot point goes right there. Why do I put it right there? Because when we figure out the torque due to this force from the wall, go back to the basic torque equation, one factor is always the size of the displacement vector that starts at the pivot point and ends at the point where the force is applied. But here, if we put the reference point or the pivot point right here, then the reference point and the point where the force is applied are the same point. So the displacement vector that takes you from the reference point to the pivot point is a displacement vector of 0 meters. So you put 0 in that slot and you get 0 for the torque caused by this force. If this force causes no torque, then there is no torque involving this unknown force. So as a result, this unknown force does not show up in any of your equations. If it did, you'd have too many unknowns and too few equations, and you couldn't solve for the thing that you really want to solve for, namely t. So let's just do it this way. Now, figure out what the torques look like for each of these three forces. As I just said, the torque due to the force from the wall must be 0. And then how about torque due to the weight? Well, use the equation here. First term is magnitude of the force. In this case, the force that we're talking about is the weight of the beam. The weight of the beam is mass times g. Next factor is the size of the displacement vector, which takes you from the reference point to the point where the force is applied, and that distance is half of the beam's length, or L over 2. Don't be afraid to put in an algebraic variable that symbolizes something you don't know. There's sometimes a powerful temptation to put in a number there, but don't, because you don't know the value of that number. So just don't, because if you do, you'll be doing something that is wrong, and you will get a wrong answer. Then we have to pay attention to the signs of torques, so that when we add all the torques together, we're adding them correctly. If we think of the reference point as a pivot point, a point where there could be an axis of rotation if the thing really did rotate. If this weight force is pulling on the beam like this, strong enough to make it rotate, it would rotate like this. It would rotate clockwise if this were an axis of rotation. Any kind of torque that makes a new clockwise rotation appear, we call that a negative torque, because we call clockwise rotations negative rotations. So negative there. Then finally the last term is the torque due to this tension force. Which is the magnitude of the force. That's the thing we're trying to solve for, so we just call it T, can't put in a number yet, times the size of the displacement vector, and in this case the displacement vector takes you from the reference point, as always, and now takes you to this point, because this is the point where the tension force is applied. So the size of the displacement vector is just the entire length of the beam, or L meters. Now, for the first time, we have to deal with this factor here. Right? In this torque, remember, angle is the angle between displacement direction and force direction. For the torque caused by this force, the displacement, which takes you from here to here, the displacement is a horizontal vector pointing straight to the right, and the force is vertical. So the angle between displacement and force is 90 degrees, and sine of 90 degrees is just plain 1, so I just didn't bother to write it in. Here, same thing, except now the angle is not going to be 90 degrees. This is obviously not perpendicular to the horizontal direction. But so the displacement vector takes you from the reference point to here, so again the displacement vector points horizontally straight to the right. So here's the displacement direction, and then you sweep through this much angle to get to the force direction. So the angle between displacement direction and force direction is this angle here. Since if you went all the way around from this direction to this direction, that would be 180 degrees. This is 30 degrees. So going from here to here must be 150 degrees. Turns out that the sine of 150 degrees is going to be the same as the sine of 30 degrees. That's just the way trigonometry works. Whenever you have two angles that add up to 180 degrees, they have the same value of sine. But I'll just leave it as 150 to make it easier to remember what that angle actually means. That is something that you need to remember and be careful and precise with it. Angle between displacement direction, in this case displacement direction is this way, and force direction, which is upward and to the left. And that's going to be a positive torque. How do I know? Well, if this tension force were pulling strong enough to make the beam rotate about the pivot point, then you're pulling up and to the left on this, so it makes it rotate counterclockwise. Counterclockwise rotations are, we define positive rotation to be a counterclockwise rotation, and so if you have a torque that makes a brand rotation here, we have to call it a positive torque. So then the net torque is just the sum of these three torques, 0 plus this plus this. So 0 plus this one, which is minus mgl over 2, plus this one, which is tension L sine 150. All right. If you ask your calculator to what the value of sine 150 is, it will tell you that sine of 150 is 1/2. And this is the beam is in equilibrium, so we know that the net torque on it must be 0. These torques must all add up to 0. And now we can solve the equation for this. We can get rid of those factors of L because there is an L factor in every term. So if we were to divide the whole equation by L, you'd have all this over L, so the L up here would be canceled out, and you'd have this over L, so this L would also be canceled out, and then you're left with minus mg over 2 plus T, canceled out the L, so then you just got 2 equals 0. Now, get rid of those factors of 1 over 2 by multiplying the whole equation by 2. And then we have minus mg plus tension is 0, or, well, obviously that means that the tension must have the same strength as the weight. This was 1,000 kilograms, and of course this is 9.8 meters per second, so you have 1,000 times 9.8, which just gives you 9,800 newtons. Okay, and then you'll try in the in the assignment one similar equilibrium problem that has one extra piece, just making it one step more complicated than this, but roughly the same idea. Now, the other thing, I wanted to go back and talk about the last question on the third quiz. Remember what was going on there. Yeah, the two tug-of-war teams, and I'll represent each team by just one person. So here's Team A pulling, and then here's Team B pulling. And Team A feels a rightward pull from the rope. Pull from a rope is tension. So here's a tension from, it's really Team B pulling on Team A. And then Team B feels a leftward pull from the rope tension. And what's the source, as far as Team B is concerned, what's the source of this force? Well, Team A is pulling on Team B. So those two forces are a third law pair. What you see here is the pattern that is repeated every time you have a third law pair. They're the same type of force. They're both tensions. They're pointing in opposite directions. This force is to the right, this force is to the left. And when one force has Team B for the source, the other force has Team B feeling the partner force. Whatever is the source of one force becomes the thing that feels the partner force. And similarly, the thing that feels one force becomes the source of the partner force. When you look at the force and then you focus your attention on the partner force, you find that the roles of source and thing that feels the force have been reversed when you go from force to partner force. So they have the characteristics. So those two tensions have the characteristics of a third law pair, and therefore you must conclude they're equally strong because they are a third law pair. The magnitude of the tension from A pulling on B, A pulling to the left on B, is the same as the magnitude of the tension from B pulling on A. You could also have so we use Newton's third law to figure out how these two forces at the two ends of the rope are equally strong. You could also use Newton's second law to explain why the two forces are equally strong. In that case, think about it like this. Here's the rope, and now let's imagine sort of the middle section of the rope as the object that we're paying attention to, and we're thinking about all the forces acting on this object. Well, what are the forces acting on this object? Other than gravity, forces can come only from things that are in contact, and the only thing in contact with this piece of rope is this piece of rope and this piece of rope. The only kind of forces ropes can apply is tension. So there's a tension force pulling to the right, pulling on at the right end of the rope. Right? This piece of rope is pulling to the right on the middle segment that we're paying attention to. So the tension force on the right. And similarly, there's a tension force from this piece of rope pulling the other way on the piece of rope that we're focusing on. So there's a leftward pull from the rope to the left of this middle segment. So those are the forces, and then we'll say that this is the positive and this is the negative direction. Do the same thing as always. Once you know what the forces are, write the algebraic expression that shows how forces combine to give you the net force. So that's all what is the net force on this. It's just a combination of this force and this force. So the algebraic expression for net force is just all the force in the positive direction minus all the force in the negative direction. And since that is a net force, it's equal to mass times acceleration. That's what Newton's second law tells us. But here's the thing. If we say that this rope has essentially no mass, it's a very flexible light rope. And implicitly, without actually coming out and saying so, that's really what we've been, an assumption that we've been using all the time so far, that that the rope doesn't have any significant amount of mass. Therefore, the weight force of the rope is insignificant compared to the strength of other forces that we're working with. But of course, if the mass is tiny, this factor is tiny, so the right-hand side of the equation is tiny, approximately 0 in other words. so this is, if this is just about 0, then this difference is just about 0. So the magnitude of the tension on the right and the magnitude of the tension on the left are just about the same. And if we use some, what you might call an ideal rope approximation, in which the rope has so little mass that you can get away with assuming it has no mass at all, then if you say m is 0, then n times a is equal to 0, so that's equal to 0, so those two would then be precisely equal. In other words, if the mass of the rope is insignificant, the tension force at these 2 points on the rope must be the same. And there was nothing special about those 2 points. I could have chosen any other pair of points and come up with the same answer, namely the tension is the same at those 2 points as well. The moral of the story is, if you can ignore the mass of the rope, then the tension in the rope is the same everywhere, and that's true because of Newton's second law. Okay, now in part 2 we'll think a little bit about momentum.